Hello everyone, welcome back. In the last couple of classes, we looked at the Euler equation as well as the Navier-Stokes equations, and then we saw that basically these equations comprise of the mass conservation, momentum conservation and energy conservation. And if you look at these equations, so what we saw that they are basically highly complicated equations. You have the term which is basically the unsteady, okay, del by del t term. Then you have terms which are depend on the space, okay, and they are non-linear because this u I multiplies to u v here. Then you have the pressure gradient term, then you have diffusion which is because of the viscosity. In the Euler you will not have this term, okay, and then you have the you may have some forces. So, solving these equations are very complicated unless you understand the character of this equation. What do I mean by character? We want to find out whether these equations come under any of the classical equations that we study in our math. For example, you might have heard about the heat equation or the wave equation, even Laplacian equation, right. So, if these things, if in certain regimes the Navier-Stokes equation can show a behavior like these equations, then our life becomes easier. If you want to solve these equations on computer, which is the purpose of this course, the computational gas dynamics course, it is very important that we understand that what kind of scheme we need to use to solve these kind of equations, and for that we have to find out whether the schemes are linear or non-linear, okay, whether the scheme is coming under category of let us say elliptic or parabolic or hyperbolic. These are the different kind of PDEs which I will come shortly. And of course, the multidimensionality is something that you cannot avoid, okay, and we have to solve especially in the compressible flows pressure and velocity in a coupled manner, right. So, let us go and see the classification of PDE, that is very important. So, what we want to get from here is basically we want to see how the PDEs behave, different kind of PDEs which you might be knowing already, and then we want to see whether there is any correspondence with the first Euler equation and then the Navier-Stokes equation, okay, so that we can devise our scheme how we are going to solve the governing equations for the fluid flows, right. So, before I go, I just want to talk about some basic things about the PDE and ODE, which is just a kind of refresher of the math course that you have taken in PDE, right. So, first of all, what is ODE in PDE? So, if you have just, so let us say you are trying to solve an equation which has got just one independent variable, okay. So, then you will have just let us for example, du by dx plus u equal to 0, something like that. This is kind of ODE, right, but if you have let us say multiple variable let us u x y, and then you, so this you can write as du by dx because the only dependence of u is on x, right, but here you have to use the partial derivatives. So, my equation like u del u by del x, okay, plus maybe x del u, yeah, by del y or something like that. So, these are basically the PDEs and these are basically ODEs, okay. ODEs are simpler to solve, okay. In certain cases you might have read about the variable separable kind of approach where you try to convert the PDE into ODE and solve them because ODEs are simpler to solve. So, that is the first basic thing. The second thing is that what was the order and the degree of an equation, right. So, the order is basically what is the highest order derivative present in the certain PDE. So, if you look at this PDE for example, okay, so the highest order is here, okay, so that is d2u by dx square. So, that is the highest order. It is true for either ODE or PDE, right. So, order is 2 here. If you look at this equation, what is the highest order here is 1, right, just one order dy by dx. If you have like let us say dq y by dx q and plus 2 d2u y by dx square, something like that, and so on and so forth, then this is basically the third order, right, because the order of this the highest order is 3, right. So, that the highest order of the derivative is the order of the PDE, okay, or ODE. And what is degree? So, degree is what is the power on which this highest order derivative has been raised, right. So, you have to see the highest order derivative, in this case it is d2y by dx square and it is raised to power 2. So, this is degree 2. Here the order is 1, but it is raised to power 3. So, the degree is 3. So, you have to be very careful to look at what is the highest order derivative first and then see the degree of that, the power of that. So, for example, if I give you a question, for example, let us say del q y by del x q plus d to u by dx square whole square plus let us say dy by dx to the power cube equal to 0. If this is the ODE that you want to solve, okay, so you can replace this del 2 with d because this is an ODE. Okay, so it is not a partial derivative. Okay. So, still the degree is 1 only because this is the order is 3, right, and that particular term is raised to only power 1, right. So, although this has got order 1 and degree 3, this particular term the degree of the PD will be 1, right, and the order of the PD will be 3. Okay. So, you have to look at the highest order term. Okay. So, these are some basics that I just wanted to cover before I go. And second is the linearity of the PDs, right. So, we have been talking about non-linearity in the equation. So, when we talked about the Euler equation, we saw that there is an advection term where the u multiplies with u, right. So, how do you basically see if the equation is non-linear, right. So, linear is very easy. Let us say you have an equation like this. Okay. So, when I am writing u x or u y, okay, in most cases u is basically del u by del x, okay, and u y is basically del u by del y. Okay. Now, this is just the shorthand expression of the same thing, right. So, if the coefficients of this a and b, they depend on only x and y, right. So, basically no dependent variable coming here, right. So, then it is a linear ODE, right. So, I can write it for example, x u x plus 2 u y plus whatever u equal to 0, okay. All these kind of things, these are basically linear PDE, right. But then let us say I change it to u x, okay. This is the kind of term that we see in our Navier-Stokes equations, okay. And then I mean rest of the terms you can keep as the same, right. So, this is no longer linear because you are trying to solve for u and then the coefficient also has u. So, it depends on u or you are trying to solve for u, right. So, these are basically kind of non-linear equation, but then it is not completely non-linear. Okay. So, the non-linearity can be of certain degree, it can be highly or fully non-linear or it can be semi-linear or it can be quasi-linear, right. So, what do you mean by semi-linear and quasi-linear? Basically, we have something called linear and then we have non-linear, okay. But depending on how much non-linearity that you have in the certain PD, your equations the behavior may change, right. If it is strongly non-linear, then what happens that your highest order derivative they appear non-linearly, okay. That means, your A may have basically u x and u y kind of term, okay. So, if I write this expression, let us say I say u x is square plus whatever 2 u y, let me keep the other term same, okay. This is a strongly non-linear equation, right. So, this you have the non-linearity in the highest order term, okay. The highest order highest derivative appear non-linearly. So, that is the completely or strongly non-linear or fully non-linear equation. Now, what I will say I go back to this example. So, let us say instead of u x I have just u x plus 2 u y plus u equal to 0, okay. So, here we have this highest order derivative, okay, but their coefficient depends on the dependent variable that you want to solve, right. So, these kind of problems are called the quasi linear, okay. I will relate it to what we have learnt so far in our Euler and Navier-Stokes. But right now, I hope you understand that this is the quasi linear where the coefficient of the highest order term does not have that same derivative or the same order as the actual derivative, okay. So, in other words, so u x is the actual derivative and it has a coefficient let us say a, it does not contain term which is u x or u y, okay. And then there is another thing which is basically the semi-linear, which is even weaker non-linearity than quasi-linear. So, let us say I will write the same thing as this one. So, x u x plus 2 u y and plus u square equal to 0. Okay. So, the highest derivative, so terms appear linearly. So, the coefficient only depend on independent variable like x or whatever coefficient constant that we may have, but the lower order terms may depend on u and maybe it is quadratic or those kind of things. Okay. So, then it is called the semi nonlinear. Okay. So, if you look at in that form of a table, okay, so I have just put all of these in the form of a table. Okay. So, this is the expression that you have, right. So, what I am saying, if it is linear, then a cannot be a function of u or its derivative. So, it can be only x or y here, same with a b c. Okay. When it is semi linear, so just one thing I wanted to say here in the last slide. So, if you want to call it completely linear, okay, then you have to have this term as only either constant or maybe x or y. You cannot have u, even if there is u, there is certain level of nonlinearity there and it will come as a class of semi linear. Okay. So, let us go to this table here, right. So, this is basically your linear and then you have this semi linear thing where the c can depend on u or x or y, okay, or their basically powers, right. So, but a and b can be only function of x or y or there will be a constant. When it is quasi linear, okay, so you the coefficients of the highest order term, in this case u x and u y, can only contain the terms which is either u or x or y, either the dependent variable that you are trying to solve or the independent variables. Okay. In the case of fully nonlinear, you have to have basically u x and u y. So, their derivative may also be present. For example, here in this case u x square plus u underscore y. So, the highest order term itself has a degree more than 1 or it can be let us say u x u y, right. So, it is not only depending on u, but their derivative also. Okay. There are I mean for certain class of problems, let us say just one first order problem, you might have I mean the different textbook might have different definitions of semi linear and quasi linear, but broadly the most nonlinear is the fully nonlinear where the highest order term has got the coefficient containing the same order derivatives, okay, and the quasi linear and semi linear, okay, are basically the weaker form of the nonlinearity that we have. So, if you look at for example, Euler equation. So, what is the degree of what is the order of the Euler equation? There is no viscous term there, right. So, there is no del dot tau term or basically the term the tau itself is a it goes as like du by dx, right. So, it is basically the second order term, second order term is missing there. So, this equation is first order, okay, and the first order term it has got one first degree because there is no power to these equations there, and this is a quasi linear PDE, right, because why, this is basically u du by dx, right. There is no term containing like say du by dx square or du by dx into du by dy or something like that. Okay. So, this is a quasi linear PDE. Okay. So, it is a nonlinear equation, but if you want to go to more specific, it is basically a quasi linear PDE. If you go to the Navier-Stokes equation, right. So, the only thing which changes is now it is a second order equation. Why? Because of the presence of this viscous term, right. In the case of incompressible, as we saw in earlier classes, this can go to basically mu del square u, right, which you can see here, which is basically mu del to u by del x square plus del to u by del y square. If it is 3D, then there will be another term del to u by del v square. This is for x momentum, then you can have the y momentum and z momentum. So, you can clearly see this is the basically second order equation, right. Again this is a quasi linear, right, because I mean here in this term if you see this is u du by dx. So, you have u multiplying du by dx, right. There is no du by dx square or d to u by dx square square, okay. There is no term which is like this or even like this. Okay. So, that is it is a quasi linear PDE. Okay. So, now that we have sorted out the linearity part, let us look the characteristic of the PDE. So, what are the characteristic? So, if you look at the Navier-Stokes equation, so what we had the first order term, we had basically u x u y term, okay, and if you are 3D then you may have u z term also, and when I say u I mean all the velocity component, you may have v, you may have w, then you have basically u x x, u x y, the cross derivative, and the uy by all these kind of second order term also, right. So, we can write basically any second order equation in a general form. This is the general form that I have written here. So, a phi x x, b phi y x y plus c phi y y, these are the second order terms. Then we have the first order the terms phi x phi y, and then we have this f y and plus g, right. So, basically as we discussed earlier, what will matter here is basically if you want to characterize this, what will matter here is the highest order term. So, we can write it as a phi x x plus b phi x y plus c phi y y, and then we can club all these together and we can call it as h. Okay. And why we are doing that, we will come to that point very shortly. So, basically we are trying to see what kind of PDEs they are. So, what do I mean by what kind of PDEs they are? So, there are certain PDEs which basically give very smooth solution, okay. There will not be any discontinuity in the solution, okay. But there are certain PDEs which allows for discontinuous solution, okay. For example, you might have heard about SOX, right. In the earlier theory you basically saw how the SOX are formed, right, and you also solve this 1D problem, okay, in the flow in the nozzle, etcetera, right. So, we are looking for basically the kind of PDEs which allow SOX, okay. And when I say SOX, it is if you look at the physical meaning of it, it is basically a discontinuity, right. So, if you know about the SOX, so for example, the SOX are basically strong discontinuity. So, you have let us say you may have so let me make it pressure or sorry velocity. So, very high velocity here. So, this is u left and u r. Okay. So, the velocity goes down drastically, the pressure may increase, okay. The pressure will increase actually, right. So, what is happening that there is a point across which this flow is discontinuous, right. So, this is basically shock. So, there are certain PDEs which may allow this, but there are other kind of PDEs which may not allow. So, when we are looking at it, we are interested in the lines or the locus of lines where we say that the derivative dy by dx either is does not exist, okay, or it is indeterminate. Okay. So, we are trying for locus of points where dy by dx is indeterminate, or you also may think of it as there are many solutions which exist and we do not know which solution to pick, right. In any case, so we need to find things about dy by dx. So, what we will do? We will write two more expressions. So, this phi x, because it is second order equations, we can write phi x in terms of x and y. So, the d phi x, okay, the first order derivative will be basically del phi x by del x into dx for a small element and del phi x by del y into dy, right, because phi x depend on both x and y. So, you can write it as phi x x dx and phi x y dy, right. So, this is for d phi x, and similarly you can write for d phi y, because d phi y also depends on x and y. So, you can write as d phi y, that will become as del phi y by del x dx plus del phi y by del y dy, right. So, that will become phi x y dx plus phi y by dy. So, you might say this is phi y x, but from because of symmetry the phi y x becomes the phi x y, right. So, then we what we will do, we will write all this in terms of, so we will collect all these phi x x term. So, we have this phi x x term here. So, let me collect the phi x x term from all this, okay, and I am writing in the matrix form like we did earlier for the PDEs. So, you have this phi x x and phi x y and phi y y, right, and you have this a, b and c, a phi x x plus b phi y plus c phi b phi x y plus c phi y y is equal to minus h. Similarly, you take this equation. So, phi x x multiplied by dx, phi y multiplied by dy, and this is 0. So, that becomes d phi x, right, and similarly, if you look at this one, so that will become 0 dx dy, and that is d phi y, right. So, we are interested in points where the derivatives are basically indeterminate, okay, So, because we want to basically separate those kind of PDEs where we cannot find the solution of this matrix or the determinant of this. Why? Because if you recall from the linear algebra, let us say you want to solve a problem of A x equal to b, right. When do you say that you cannot find the solution of x, right? When the determinant of, if you know the Cramer's rule, is basically 0, right. So, same thing we are going to do here. We are saying that okay, these derivatives phi x x, phi x y and phi y y, these derivatives do not exist or they are indeterminate when the determinant of this part is 0, right. So, we are going to see the property of this determinant, right. So, if you do this determinant, let me go there. Okay. So, you had this expression a b c and then basically dx dy, let me write determinant 0 0 dx dy, right. So, then what will happen if you do that? So, this is a dy is square, okay, and minus b into dx dy, okay, and plus c dx is equal to 0, and then you divide everything by dx is square. So, that will become a dy by dx is square plus b dy by dx minus by dx, okay, and plus c is equal to 0, right. So, and the value of this will be given by this, okay. Yeah. Okay. So, this is the line, this is the line which says if you have a line of this slope dy by dx, okay, then it says that across this the derivatives like phi x x, phi x y and phi y y are basically undefined. Okay. So, if these lines exist, okay, then your solution may have the discontinuity or it may form shocks, right. So, when we will let exist. So, let us say if my value which is under square the root b square minus 4 a c, if it is less than 0, then this will become imaginary, right. Then the real solution of dy by dx will not exist. So, there is no real characteristic and we call that as an elliptic equation, right. When this becomes to 0, right, then you have just one real characteristic, okay, and then we call this as a parabolic equation. And when this value inside the under root is basically greater than 0, then it's the entire thing is real, and then you have this minus b plus minus square of whatever value, let us say b square minus 4 is equal to 4, then it will become plus minus 2, right, by 2a, and a and b both are real. So, then dy by dx will be the real value. In case of there are two real characteristic, there are two directions in which it can propagate, and these kind of systems are called the hyperbolic systems. Okay, we will get into these things shortly, right. So, the question is how do you get these names elliptic, parabolic and hyperbolic. Many of you might be using these terms already for PD, but where do you get this nomenclature? It basically if you look at any conic section, right. So, they are given as like this. So, you may have ellipse, parabola, hyperbola. So, this is a x square plus b x y plus c y square plus whatever the smaller order terms, okay. And you say that okay, when b square minus 4 a c is equal to 0, then it is a parabola, right. And then when it is less than 0, greater than 0, then it can be ellipse or hyperbola. So, the nomenclature has been taken from here. So, now instead of a x square plus b x y plus c y square, this kind of quadratic equation we have basically a PD a phi x x plus b phi x y plus c phi y y, but we still see the characteristic dy by dx and we say whether it has got 0 or 1 or 2 real characteristic, right. So, now let us look at some of these. So, one is let us start with very simple equation that you know. So, let us look at the first equation which is the Laplacian equation. Okay, you all know this is del square phi equal to 0. Okay. So, this is the Laplacian equation, right. So, if you compare with this a phi x x plus b phi x y plus c phi y y is equal to minus h whatever it is, right. So, the a is equal to 1, b is equal to 0 and c is equal to 1, right, compare the coefficient here, this is 1 1, right. So, then you can do b square minus 4 a c, that will become as minus 4, because both a and c are 1, right. So, this is less than 0, that means the real solution of dy by dx will not exist, right, and this kind of systems which are governed by Laplacian equations are called the elliptic system, or these equations are called the elliptic PDEs, right. So, where do you see this kind of elliptic PDE? So, this is basically what it is saying, and it is an equilibrium. Okay, let us say you let me say that, okay, let us say you have a body like this, okay, and you suddenly raise the temperature here, okay, or just heat it up here, it will immediately propagate everywhere until it attains the equilibrium, right. So, this PD governs the final stage where it is in the equilibrium, it is a steady state, okay. There is no time derivative here. So, it is a purely boundary value problem, okay. So, and the other thing that you might you may notice here is that the characteristic, the dy by dx is not finite, okay, because what we saw from the analysis that this is less than 0. So, the wave speed is not finite. So, in other words, the wave speeds are infinite. So, any disturbance that you make in the system which I am showing here, it will be felt instantly everywhere, okay, and everywhere it will propagate and it will equilibrate, okay. So, it will not allow any discontinuity in the domain, okay. So, this kind of systems are called the elliptic system. You cannot there cannot be any shocks in the system which is governed by the elliptic PDE, okay. So, the heat equation, for example, steady state heat conduction, you might have seen this term. So, basically del square k del square T is equal to 0, okay. So, these kind of systems are basically on the Laplace equations and or the elliptic PDEs, okay. And incompressible potential flow also, they are also are governed by this elliptic PDE, okay. So, del square phi equal to 0, okay. In electrostatic you have many problems where they are governed by the elliptic PDE, okay. So, you have one kind of scheme for this kind of problem, because whatever disturbance or whatever change you make at one point, you expect that it is felt there everywhere infinitely, I mean at an infinite speed. Of course, the infinite is not possible when you are trying to simulate this kind of problem, but the idea is that the wave speed is if you are solving it numerically, you have to have a grid where if you put a disturbance, okay, and all the grid points around that feels the disturbance instantly, okay. So, you have to have that kind of scheme, okay. So, Poisson equation, another thing, pressure Poisson which people use to solve the incompressible equations, they also come under this class, okay. The second is the heat equation, okay. Now, this is unsteady heat equation, okay, or it is also called the diffusion equation. So, you have one time derivative term which is first order and second order term which is in the space, right, and this can be the diffusivity, alpha is the diffusivity, right. So, compare with the same thing here, okay. So, you can take maybe the x as x and t as I mean y, right. So, this alpha is phi x x, alpha phi x x, a is equal to alpha, and b and c both 0, because there is no phi x y term or phi y y term, right. So, you do b square minus 4 a c, it becomes 0, right. So, these kind of problems are called the parabolic problem. In fact, a more accurate way to tell about it is that it is basically parabolic in time and elliptic in space. So, how is it different from the elliptic problem that we just saw? So, here it allows basically let us say you are trying to solve the heat equation problem and you give some disturbance, and that is the term which is governed by dt by dt, and then it will diffuse, the del 2 t by del x square will diffuse everywhere, okay, and how it is diffused is governed by this parabolic problem, okay. So, it has, as we discussed earlier, it has got one characteristic, and what is that one characteristic? So, in this case, for example, t equal to 0. So, there is just one discontinuity which is at t equal to 0 at in the beginning itself, right. So, let us say you have a flat plate or something like that, or t equal to 0, you give some disturbance in a plate and give some temperature or raise the temperature, and you see how it is, what is happening. So, that will be governed by this heat equation. So, there is just one disturbance or the one discontinuity which is allowed, at t equal to 0. We will see that if you solve the boundary layer equation, the t is basically played by the boundary layer, I mean the beginning of the plate. Okay. So, the t is replaced by an x there, but there also all the information is travelling after x greater than 0. It cannot go to x less than 0, it cannot go to t less than 0, because that is not allowed, it is a characteristic, okay, and there is a discontinuity there. Okay. So, these kind of problems are called the initial boundary value problem. Initial problem because you have to give something as t equal to 0, right, and boundary value because you have to provide the boundary condition. Okay, the last one which is most important, which will be basically discussing throughout this course, is the hyperbolic problem, and you can see it by just looking at this 1D wave equation. So, if you have a string like this, okay, and you give some motion like this, and then how it vibrates will be basically the motion of this string will be governed by this wave equation. Okay. And you can write this equation like this, and then you can say that x is my x and y is my t, right, and you compare with the same a phi x x plus b phi x y plus c phi y y, and say a equal to c square, b equal to 0 and c equal to minus 1. Okay. And if you when you collect it, this is b square minus 4 ac, which is 4 c square, which is a positive number, okay, because c square is greater than 0. That means your dy by dx that we had here, in this case it is dt by dx, okay, that will be a positive value, right. That means you will have two real characteristic, two directions of propagation, okay, and there are basically two discontinuities, I mean the discontinuities are allowed on this problem. Okay. So, it governs the wave propagation, the sound waves. Okay. If it is non-linear, and you will see that it also allows shock waves kind of thing, right. So, these are the basic thing, just let me show you a difference among these three. Okay. So, the discriminant d is less than 0 in elliptic, 0 in parabolic and greater than 0 in hyperbolic. There is no real characteristic in elliptic, you can have one family of characteristic in parabolic and two families in hyperbolic. Okay. And then this is very important. Okay. So, the elliptic only is allows the smooth solution. Okay. In parabolic, as we told that it is actually elliptic in time and parabolic in space. So, this is basically smoothing in time, and in hyperbolic allows shocks or discontinuity. Okay. And the propagation speed is infinite in elliptic, okay, and the diffusive term in the parabolic is also infinite, okay, but hyperbolic there is a finite speed. Okay. And then the time dependence are essential. Sometimes the space can play a role of time. What do you mean by time? Space can play a role. That means that just like the time cannot go negative, the space also cannot go negative. So, basically it has to go from a certain space, right, certain boundary. Okay. So, yeah, the examples we discussed, the Laplace and heat and wave and Euler. Okay. The elliptic is basically a boundary value problem, parabolic is initial boundary value problem, and hyperbolic is an initial value problem. So, we will stop here. In the next class, we will look at some more equations which represent the hyperbolic system and even also the elliptics or parabolic systems, and they will look into the Euler equation, whether they represent or whether they fall under any of these categories. Okay. With that, thank you very much.